Hey, so you've gone through the introduction to scheduling, and the next logical place for us to go is to look at critical path analysis. So critical path analysis, it's kind of deserves to be off on its own because it largely is a technique which is going to allow us to determine what the critical path is of the network, and we'll talk a little bit more about what that is. I know we mentioned it, and so that process, that technique. It's worth understanding. It's also largely automated in a lot of computer codes that you might use to support your project management scheduling. But at the same time, I think it really is important that you understand what is going on and what the various terms mean. And then, as we look at some of the outputs from the critical path method as they're overlaid onto our Gantt chart and whatnot, it starts, we can better appreciate what it is we're doing when we start to mess with it and start to move things around and make decisions because of what it tells us. So let's get on with looking at the critical path method and the mechanics of making it happen, and then we'll finish off this lecture with a little bit of a discussion of, I guess how it empowers you to make informed decisions. So the one thing that we need to start is every activity needs to have a time estimate. It's a single number that goes into it. Now, whether you arrived at that number using PERT or some other mechanism, it doesn't really matter. But going into the critical path method, we do have to have a single time estimate for each of our activities in the network diagram. And what we're going to do is we're going to use this process to identify the earliest and latest a project or an activity can start, as well as the earliest and the latest that it can finish, based on the precedence of the activities that lead into it and follow it. And whether or not there is any slack that you have, is in maneuver room to, purposely schedule that activity, to the left or to the right, without affecting the overall project length, which is one of the goals of why we're doing the CPM. So in doing this, we will identify the critical path, and I show critical path in red, and you'll see, like a lot of defaults in software and everything else, quite often we always highlight the critical path in red so that we're always aware of what is or what is not on the critical path. So what is the critical path? Just to reiterate from the introductory lessons, it is the longest path within our network. So we're starting with our network. It allows us to identify the longest path in time to pass through the network. And thus it represents the shortest time in which the project can actually be completed. But what it also tells us is that if there is any delay along the critical path, that we will actually be delaying the overall duration of the project itself. So when we talked about that slack, that room of maneuver that you can have to shift an activity one way or the other in time, the one thing that identifies a task that's on the critical path is that it has no slack. You can't deliberately move it at all without having an impact on the overall project. So we're going to use our network diagram, and so to see the mechanics of getting the critical path determined, I'm just taking my node. So this is that node that had the activity letter in it, and I'm just going to expand it because we're going to carry more information in it through this process. And what we're going to do is we're going to identify the earliest start and the earliest finish, and we're going to use these two, not quite quadrants, but almost quadrants to contain that information. And we're also going to have on the bottom half the latest start and the latest finish. And we'll see this is a two-pass, sort of two-stage process, and we'll fill all of these out in those two stages. So the earliest start and finish steps, or the forward pass. So like I said, this is a two-pass or two-stage process. We're going to pass through our network from start to finish, and we're going to work along the top half of all of our nodes determining the earliest start and the earliest finish for each of our activities. So at the beginning, we start, the earliest our start activity can start is time 0. And then the earliest any activity can finish is its earliest start plus its duration, right? So the earliest it can start plus its duration equals the earliest time it can finish. And so the earliest time an activity can start later in the diagram is the largest of, or the maximum of, the earliest all of its predecessors are finished. And we'll see that. And so this forward pass, we're basically going to go through the network along all of its different branches until we get to the end, doing this basic comparison and calculation as we go through it. So let's start with our start node. So it has a duration of 0, and it also has an earliest start of 0 because it's the start node. And so we already know that to determine the earliest finish, what we have to do is we have to take that earliest start of our activity and add its duration to it, and that will give us our earliest finish. And we'll fill that in the top right space or quadrant as the earliest finish. And now what we need to do is pass on to its successors and carry on through the network to determine the earliest start and earliest finish for every node. So let's draw out our diagram. So this is the same network diagram that we did in the introductory example. And we see all of the activities from A through H, including our dummy activity for the start. And I've already filled out the start as earliest start and earliest finish as zeros from the previous slide. And so now we're ready to move to its successors. We'll start at A and then go to B and then through the network. So if we look at A, we have to figure out what the earliest start is of A. The earliest A can start would be the latest or the largest of the earliest finishes of any of its predecessors. So in this case, it only has one predecessor, which is the start dummy activity, and it has an earliest finish of 0. And we've got to put in all of our activity times. So those are the durations. And so we fill out 0 as its earliest start, and because we know its duration, we can automatically just add one to the other to get its latest or earliest finish. Now we'll go down to node B, and we see it also has an earliest start of 0, and that gives us an earliest finish of 3 by adding its duration to it. And we'll just start working our way through the network. And so if we get to C, again, we take the 2 from A. That's the earliest finish of A. There's no other predecessors. So we put in the 2 there, we add its duration to it, and we get an earliest finish of 4. And then at D, for the first time, we actually have 2 predecessors coming in. And so to determine what the earliest start is for D, we have to take the maximum or largest of the earliest finishes of its predecessor. So A is 2 and B is 3. So we take the larger of and we bring 3 in. And it just makes sense that the earliest it can start is when all of its predecessors are completed. And so it can't start after A is finished. It has to wait for B. And so it gets an earliest start of 3, adds its duration to it, and gets to 7 for its earliest finish. So now if we pop up to F, again, we take the 4, the earliest finish of 4 at C, and we bring it over to the earliest start at F. We add the duration, we get to 7. We'll do the same thing at E. 4 plus 4 is equal to 8. And then now if we go down to G, again, we have 2 predecessors. So we're looking at E, which has a earliest finish of 8, and D, which has an earliest finish of 7. We know we're going to have to take the larger of, so we take the 8, add the 5 duration to it, and we get an earliest finish of 13. And finally, at our last activity, again, 2 predecessors, F with an earliest finish of 7, G with an earliest finish of 13. We have to take the larger of, and so we take the 13 from G, add the 2 duration to it, and we get an earliest finish at H, and indeed for our entire project, of 15. And so that is the forward pass. And with the forward pass, at the end of the forward pass, we have the earliest start and earliest finish for all of our activities, including the time that it's going to take to do the entire project in the, if everything goes off as planned. So now that's the first pass, if you will, or the first stage. So we have to now do the second tier, which is the backward pass, and that's going to allow us to determine what the latest finish and latest start is. I say them in that order because we're working backwards through the network diagram. The latest finish is the of our end, because we're starting at the end and working forward, is the maximum earliest finish for any of the activities. But because we're going to have a logical node there, if we have multiple finishes, we're going to put a logical finish. So whatever its earliest finish is, that's where we're going to start. We're just going to carry that number down, put it into our latest finish, and then work our way back. So having a latest finish, we get to the earliest it can finish by subtracting its duration from it, because if this is the latest it can finish, subtract the duration, we get to the latest it can start. Hopefully I said that right. I didn't stumble on my words. And then as we go through it, of course, now we're carrying information from the successors, not the predecessors, but the successors forward. And so the latest start for any activity that has multiple successors is the minimum latest start coming forward. So we're going to proceed, like I say, from the back all the way forward, working down the bottom half of all of our nodes. So the easiest way to do that is, again, by an example. So let's take our major node, our finish node. We've already got the earliest finish, and we know that we can bring that down and fill out our latest finish. So the latest finish is the minimum latest start of following activities. There's no following activity, so we just bring down its latest or earliest finish. And then we subtract the duration from it to get its latest start. So let's go back to our network diagram. So here we have our network diagram, and let's fill in H because we've already done that. And now we can start working our way through. So we'll go down to G. And so we see that we have a latest start of H of 13, and there's no other successors, so we can bring that down to the latest finish of G. And fill in 13, then we can subtract its duration, and we'll get 8 as its latest start. And so from there, let's go up to E. And so we only have the one successor. We know that this latest finish is going to be the value then of the latest start. From G, we put it in, subtract 4, we get 4, and we'll wander down to D. So in D, we only have a single successor again, so we can take the 8 from the latest start of G and bring it over as the latest finish of D, subtract its activity or its duration, and get its latest start. The terminology, tripping all over it all the time. So let's, we've gone quite a ways there. We need to work the upper part of the diagram. So let's look at activity F. In this case, we have a single successor. So we have 13 at its latest start. And so we'll bring that up to the latest finish of F, subtract its activity time, and we get a 10 for its latest start. Now, if we look at C, we're going to have two successors in this case. And so we have two latest starts. We have 10 for F and 4 for E. And so we have to take the minimum of those two, and that would be the 4 from E would come over and be the latest finish for activity C, and subtract its duration, and we can get its latest start. So we can look at activity A, We can bring over the 2 from C, subtract that, we get 0, and finally we'll fill out activity B. Again, a single successor, so it's easy. We bring over the 4, subtract the 3, get the 1, and we just have our start activity to finish, and it goes down to 0 and 0. So that's our network diagram with all of our earliest starts, earliest finishes, latest starts, and latest finishes all fully filled out. So now we want to look at a comparison of those numbers to figure out what a critical path is. And to do that, we have to consider the concept of slack again. And as we talked about, slack is the length of time an activity can be delayed without delaying the entire project. So only activities that are not on the critical path have that flexibility. By very definition, if something is on the critical path, it can't be delayed without delaying the overall project. So what we need to do is compute the slack, and we can do that one of two ways. It's either the latest start minus the earliest start, or the latest finish minus the earliest finish. You'll get the same answer no matter how you do it. And as you would expect, any activities with a slack time of 0 are on the critical path. And so if I take our table that we were working on for that example problem, and we lay out all of the activities. So we take the early start, earliest finish, latest start, and latest finishes from our network diagram. We fill all of those out. We do the calculation of slack, and you can see which ones have 0. And of course, I've colored them all red because I now know that wherever that 0 slack is, that's on the critical path. And so with that information, I can now actually draw graphically the critical path through my project. And so we're back into our network diagram, and I'll lay out all of the slack calculations, so the slack for each of the activities shown. And so what I need to do is to draw a path or paths, there can be more than one critical path, through the network wherever the slack is equal to 0. And so I'm just going to work my way through there, identifying it and drawing it red so that I know where my critical path is. Now, this is the critical path method. This is how it was developed. It works using the network diagram, but it gets really, really useful when we put it on to our Gantt chart, because what we really want to get a better feel for is how we can use this slack and how it interplays with the activities around it to inform our flexibility when it comes to non-critical activities. Critical activities, we know that we want to do everything we can not to delay them, give them the priority so that our overall project is not delayed. So let's go back to our Gantt chart and see if we can't overlay this information in a Gantt chart format. And so the traditional Gantt chart that we've looked at so far would basically be represented by doing an earliest start, earliest finish transfer of all of these activities onto the calendar. And so here we have our Gantt chart, or the structure of our Gantt chart laid out. And what I want to do is I want to overlay each of our activities, and I'm just going to transfer them to the Gantt chart based on their earliest start, earliest finish. Now, as I did in the table, I've already identified my critical path activities as red. And so we know that their latest start and latest finish of all of the critical activities is going to be the same as the earliest start, earliest finish, because there is no slack. And so they're not going to change whatsoever. But what I want to do is I want to get a feel for the slack. And to demonstrate the slack on the Gantt chart, what I want to do is I want to add to this or show what would happen to my non-critical activities if I plotted their latest start and latest finish. And so here we have this set up, and to plot that, again, only looking at the non-critical activities, I'll start at activity B, and if I shift it to the latest start and finish, but keep the information of where the earliest start and earliest finish was, you now get the idea of what room it has to move without affecting the critical activities around it. And I tend to think of it almost as a little slider. So I can now slide activity B within that range from 0 to 4 without affecting the critical path. And let's do the same thing for activity D. And activity F had a lot more slack. And so you can see what room or flexibility, what maneuver room you have in scheduling the non-critical activities without affecting the critical path. So one of the weaknesses that we identified in the Gantt chart was that it didn't show predecessors. And so this has limitations as far as understanding the impact of shifting things around when you're just looking at the Gantt chart and not looking at the network diagram. But as you would expect, there's no reason graphically that the computers can't show predecessors on a Gantt chart. It just wasn't done in the initial form. And so most would show those predecessors. And so I'll just draw them in here. So coming off the end of these activities, showing which activities are connected to it and doing that logically in the software, of course. Now, this information is going to become really, really valuable to us when it comes to dealing with some of those over-constrained resources when we start looking at resource scheduling, because if we don't have enough resources that we can't do everything at the earliest possible start, we want to know what maneuver room we have to shift things around to try to make them available for, or to line up when they're scheduled with the resource availability and keep our project on schedule. Now, with the predecessors shown, if I start to slide my non-critical activities, you will see that the rest of the diagram updates itself. So if I back up again, so I have activity B, if I start to move activity B for resource reasons or otherwise to the right, we can see that once I move a full day, activity D gets pushed with it because of their predecessor arrangement. And eventually, if it goes the full day, activity D now becomes a critical activity and joins a critical path. And we can move activity F and move it over. So the other thing I wanted to talk about, so we've been talking about predecessors and successors. They're all nose to tail, as in one has to be finished completely before the other one can start. And that's the way the network diagram was kind of conceived and designed. But certainly with the software tools that we use today, we can have a great deal more control over what the various predecessors arrangements are, including any lag that we may want to program in. So if we look at it, so if we think of activity A, the traditional one would be shown as a finish one before you can start the next, and it would be shown like that. But we can also accommodate ones that you need to have started the other one before this one can start, and that would be a start-to-start relationship. It's also possible that you would have a finish-to-finish relationship where one needs to be finished before the other one can finish. And so that would be a finish-to-finish relationship. And then we can incorporate any lag. So in this case, I'm showing a finish to start plus lag. And that could be anything from, let's say, the activity E is building the walls, whereas activity D was pouring the foundation, but we need to give ourselves at least 3 days for the concrete to set up before we're ready to build our walls. And so we could have a finish to start relationship, but we know there has to be a time lag in addition to that needs to be incorporated. And we could do minus lag as well, where something would precede the finish. It just it can start, say, within 8 hours of the other one finishing or something like that. And really, we can use lag, plus or minus lag, with any other precedence relationship and program those in. And so it gives us a great deal more fidelity that we can apply to the precedence relationships than we originally had with just the original critical path method. So that's really the critical path method. And it is a mechanical process, not a particularly difficult mathematical process to do the forward pass and the backward pass and doing that. Of course, it is integrated into most of our softwares that we would tend to use these days for doing scheduling. But it's now appreciating it and learning to harness it And probably the biggest challenge to harnessing it is to disassociate yourself from your biases and preconceptions and not forcing a relationship that doesn't actually exist. It only exists in your mind rather than in the physical reality. And sometimes that can be challenging to get to. I can think of one example where somebody might assume that your underground utilities have to be done before you do your foundation. And that's normally true and certainly makes a whole lot of sense, but it's not a physical requirement depending on the method that you choose. And so it can get challenging to step outside of your preconceptions to make sure that you're not over-constraining yourself beyond the actual physical limitations. And harnessing your precedents and then using the information it gives you effectively when you're tracking through the execution of your project, because you now have your critical path. You know that in all likelihood you want to protect your critical path in all instances. You have information about the slack or the maneuver room you have with your non-critical activities. And keep in mind, this is still fairly unconstrained because we haven't overlaid resources yet onto our schedule. And so that's the next step, is to overlay resources. Before we get to resources, though, we're going to take a step out. We're going to look at the application of PERT because we want to look at some refinement about how do we estimate our activity durations and how we might use that information to estimate the probability of completing our project on time or within a week or two of the scheduled time. So we're going to do that. We're going to do PERT, and then we're going to start looking at resources shortly after that.